Thanks for the organisers for giving me a chance to talk about the ACT SZ cluster survey. So we've had ACT mentioned a few times so far this week, and it's this 6-meter telescope in Chile. This is the ground screen. The telescope is sitting inside there. And ACT collaboration, about 70 people, I think, from all these different institutes. And the PI for things like ACT Poll, Advanced ACT is Susan Staggs. And there's a few other ACT people here as well, like Lyman, John Sievers, and so on. Okay, so ACT has been going for a while now. So this is what the telescope itself looks like. But things have changed a lot with the detectors over the years. So the receiver, the original receiver was called MBAC. And then from 2013 to 2015, we moved on to ACT Poll, something which is polarization sensitive and more sensitive generally. And then since 2016, we've been observing with this thing called Advanced ACT, which has got more frequency channels, more sensitivity. And that's actually been extended. It's going to keep observing till 2021, I think. And so the key point of building a telescope like ACT, it's got arc-minute resolution, the frequencies which are of interest for the SZ effect. And this is just illustrated here. This is more jerky than I expected. But on the right here, you've got the Planck map. So this is a visualization by Sigurd Ness. This is Planck, this is ACT, and then you're going from roughly of order 10 arc-minutes resolution to about 1.5 arc-minutes over here. Maybe if you squint, the most obvious thing you can see popping up as you switch over to ACT is things like point sources, so it's a lot easier to see those. And if you really squint, you might see some Sunyaev-Zel'dovich, so SZ clusters in there. So I'm not going to introduce the SZ effect again because we've talked about it a lot. But at 150 gigahertz roughly, these are going to appear as cold spots. So if you squint, maybe you can see one in that. Okay. So we've done a fair amount of cluster work in ACT. So this is just a list of some of the stuff we've done based on the original ACT sample. So this is just the cluster work. There's been lots of other work on, obviously, the CMB power spectrum, sources, and all of that. So I'm just highlighting here our last cluster cosmology results. So that's a while ago now. It's 2013. We're working on a new analysis for ACT Poll and so on. But this just highlights, so back in 2013, this main systematic, if you want to do cluster cosmology. So we hedged our bets a bit back then, and you've got different assumptions for what the scaling relation is here, and this shows the effect what that has on the parameters, sigma 8 and omega matter. And then we've done lots of other stuff. So one of those things was looking at the clusters we find. Probably the most famous one, I think, is probably El Gordo. So this was found in the original ACT South survey. This paper by Felipe Menanto in 2012, showing this is a crazy merging cluster at redshift 0.9. Okay. So moving on to ACT Poll, this is this new receiver we've had, and there's been a number of results come out so far. These are all based on the first couple of seasons of observations, so from 2013 and 2014. So if you want to read about the power spectrum stuff, that's there. There's a KSZ paper here. There's probably a couple more. In terms of the cluster search for ACT Poll, so we put out this catalog last year. That's based on this equatorial field here inside this weird black shape. And what this actually does is it coadds the original ACT equatorial survey with ACT Poll. So ACT Poll observed this bigger patch here, and we've got a survey area for this catalog of about 987 square degrees. So the nice thing about being on the equator is you've got overlap with some of your favorite optical surveys. So SDSS pretty much covers all of this. Stripe 82 is there. And we just highlighted HSC. So later on, I'll say a little bit about the weak lensing mass calibration we've done in HSC with a tiny overlap, actually, only about 28 square degrees. The DES survey region is highlighted with the dashed lines here. So we didn't actually use that for the previous ACT Poll catalog. The DES data release hadn't happened yet, but in any case, we've now got an MOU with DES, and we're working on a lot of different projects with them. And so when I show the advanced ACT clusters in a bit, a lot of those redshifts are coming from DES now. Okay. So just to show how we went about finding clusters in the most recent catalog. So again, we were still restricted to a single frequency in this case, about 148 gigahertz. And this is what one of our maps looks like. So this has got, this is the CMB. And if you look closely, at this frequency, you should see clusters as little cold spots. And so what you do is you run your match filter over that. So it's just a spatial filter, and your clusters pop up. And hopefully, if you go away and you look in your optical surveys, you find a cluster where your SZ blob is. So this is actually an image from SDSS. This is actually the highest signal-to-noise cluster in the ACT sample. So a previously known cluster, it's an RCS2 cluster at redshift 0.7. Despite that, you still see it in SDSS. So SDSS has been really handy for getting redshifts of, you basically get everything up to redshift 0.5 and a little bit beyond that as well, for some cases. So, so this is just some examples of some clusters in SDSS. Well, one factor with SDSS is, say, RedMapper, all these other optical cluster surveys have gone away and found pretty much all the optical clusters in SDSS. So you don't find many new ones in this field at lower redshifts. But a nice thing about SDSS is that we also have this 80% spectroscopic redshifts for the clusters in the sample. But for our sample, redshift 0.5, which is about your SDSS limit, is roughly the median redshift. And so we did some more observations for more distant cluster candidates using the SOAR telescope in Chile, and we used the APO 3.5 meter to get K-band imaging in some cases. And for a handful, we've got some salt spectroscopy for some things which are redshift 0.8-ish. Okay. So this is what their sample looks like. So as I said, the median redshift is about 0.49. We've got 182 clusters, only about 28 of those turn out to be new discoveries. And on the right here, I've got the mass distribution for the sample. So in this case, the mass calibration we're using, our sort of baseline fiducial mass model, is this universal pressure profile model, which is used by Planck also. And yeah, so that's what's plotted here. But as we've seen in other discussions, what we've had so far this week, if you look at the weak lensing masses, you get higher masses than what you get from this baseline assumption. And so this plot is the mass versus redshift plot for the ACT pole sample. And now I'm plotting a mass which has been indirectly calibrated using weak lensing, using the overlap between RedMapper, which has got a weak lensing mass calibration. So this is indirect, but this gives you a similar scaling to what people have found actually from doing the direct weak lensing mass measurements. So one thing to take away from this plot, as we've seen similar versions with SPT earlier on in the week, is SPT and ACT, you get a nice, reasonably flat mass-limited selection in terms of redshift, but you don't see that much at low redshift because you get confused by the CMB blobs, whereas with Planck, they've got, they can do the component separation, they can see much larger angular scale, low redshift clusters, but then they have this disadvantage that they find it harder to see the high redshift lower mass clusters. So we've been doing some follow-up studies of this cluster sample. We had one of those mentioned yesterday. So in Sushmita's talk, she mentioned the splashback work, which is done actually in collaboration with ACT, SPT, and DES. But the first result in terms of follow-up of this ACT pole sample we've had out is this one. So this is a paper led by Hironaomi Miyataki and Battaglia on doing weak lensing mass calibration with HSC. So this is just the final result, as it were. So it's a stack of 8 clusters and 11 sigma detection of stacked weak lensing. And this is the result compared to lots of different things in the literature. And so you can see we've got a fairly chunky sized error bar here. But you know, this is fairly consistent with what other people have found. And down here is this band for how you would need to change this mass bias to get it to match the Planck primary CMB estimates, inferred estimates. So you can see that's not a hugely significant difference at this point, but what'll be nice is to go away, and as we build up these weak lensing samples, these error bars are going to come down, and if that persists, then that's maybe going to be telling us something interesting. So one of the ways in which to get a bigger sample of clusters is to go away and observe a bigger part of the sky. So I mentioned our current overlap with HSC was only about 30 square degrees in that paper. We can get a lot more clusters by observing more of the sky, and in future, that's going to overlap with, you know, DES the wider HSC survey and all the rest of it. So this is a map from AdvACT. So this began in 2016. It's produced by Sigurd Ness, Simone Iola, and John Sievers. This is our main map-making guys there. And this is 18,000 square degrees, and we've got two maps at 150 gigahertz and 90 gigahertz, which we've been using as part of the ACT cluster search. So what I'm going to show in a second is based on data adding in ACT, advanced ACT poll, and then the advanced ACT data from 2016 only. Okay. So this is running the sort of match filter algorithm similar to what's been done for ACT poll, but over these huge maps, these huge co-added maps. So on this, we've got the Planck 353 gigahertz, and then the little blue crosses on this, each one of these is a galaxy cluster, which we've got optical confirmation for and a redshift estimate. Okay, so there's more than 1,500 of these objects. Okay, you can see here there's the outline for DES. The DES tank is in there somewhere. Up here we've got SDSS. And from the density of the points, you can infer, right, that our sensitivity is varying quite a bit over this huge map. So you can see where our deepest regions are. Okay. So if we go away, run our machinery to generate mass estimates, this is what this looks like now. So this is a similar plot to what was shown before, but now we've got about 1,500 clusters on this, drawn from this survey area. So about 14,000 square degrees. And what I just wanted to highlight here is we're doing, so you can see things are getting emptier over here. Some of that is due to the incompleteness of the follow-up. So from DES, which we've got overlap with about 4,000, 5,000 square degrees or something, that gets you redshifts up to about redshift 1-ish, pretty straightforwardly. But to go to higher redshifts, we need to look into the infrared data, which is something we can do with WISE. Maybe that can get us to redshift 1.5 for some of them, most massive, obvious things. And one thing I wanted to highlight here is this redshift 2 cluster. So this is a previously known cluster detected by XMM LSS in the X-rays back in the day. It was subsequently confirmed in SZ as well using Karma. So this is this Mantz paper. And we detect that in advanced ACT as well. So this is a 6 sigma detection. So, you know, this is a nice illustration that if a cluster is sufficiently massive, we should be able to find it if it exists. And yeah, so we've got to do a fair amount of work, I would guess, filling in this region. Yeah, so there should be more clusters there. Okay, so this is a plot which arrived yesterday. So this is, we can also look at making Y-maps. So this is work by Colin Hill, Matt Madavashiril, and Sigurd Ness. And so what they've been doing is combining the ACT maps with Planck. And so with Planck, you've got all the large-scale information. If you can combine that in an optimal way with ACT, where you're really good on the small scales, you can make these nice Y-maps. So this is just a zoom-in of a very, very preliminary map they've been making. And what's nice about this is here we've highlighted, there's a nice low redshift cluster. It's also detected by Planck, Able 119, and so this is the Y-map. So red here is where you're seeing potentially clusters. So I'm going to stress this as preliminary, but it's looking very, very promising. So the idea is to use this kind of data product in some of our analyses with DES as well. Okay, so just before I finish, I just wanted to say a little bit about Meerkat. So I'm from South Africa. This is a photo of Meerkat, which is this new radio telescope, 64 dishes in the Karoo. This is now up and running and taking data. And we're interested in using this to do a lot of cluster studies, particularly with advanced ACT. And some of this is going to be done in collaboration with people at IUCA. So there's a guaranteed time project called MARS, which is a quasar absorption line survey. But because Meerkat has this huge field of view, like a degree or so, then you can detect a lot of clusters serendipitously in those observations. And we're also going to do our own targeted observations. And the kinds of subjects we're interested in is things like the diffuse radio emission. So my current postdoc, Kendra Knowles, has been working on GMRT studies of ACT clusters. So if you're interested in that, you can see this paper. We're also doing this for the ACT poll sample, and we're going to try and do this with Meerkat for advanced ACT. Other things we want to look at is star formation, how that evolves. maybe that'll have some impact on our SZ selection. Maybe you can say something about that. I've seen a Planck paper about something about that. And then more in the future, when the polarization stuff is sorted out, we can do polarization measurements. We should be able to, you can imagine being able to measure magnetic fields of clusters in bins of mass and redshift by looking at the polarized sources along different sight lines through the different clusters. So that's the kind of thing which we want to get into. Okay. So yes, I'm just going to finish there. I don't know, 2 minutes. So I'll just leave my summary there and stop. Thanks.
Thanks a lot. Maybe time for one question while Tarun is setting up. Joel?
Very last line there.
Where's Tarun?
14,000 square degrees.
Yeah.
You had 18,000. So is that the sort of the effective area that's left?
Oh, so the 14,000, if I go back to my plot with all the little blue points, I drew a black outline. So that's kind of the area I've used for searching for clusters. So that 18,000 square degrees includes the galaxy. So possibly if people can think of exciting things to do with the galaxy, they can talk to people. But there's a lot of galaxy in that map as well. Yeah, that's what I've cut based on just, yeah, this has not been done in a very sophisticated way at this point, but just drawing around where the dust is, basically. Yeah.
I think we have time for one more question since Tarun is just setting up. Okay, let's thank